Assalamu alaikum. Hello everyone. This is Ali Bakshi from IEEE KFU student branch. Thank you all for joining us today in our webinar in photonic devices technology. And I'd like to introduce you to our speaker for today, Professor Hesham Enshasy. He's PhD graduate in engineering physics from McMaster University in Canada. He has many researches in the field of photonics, and currently he is a professor in the electrical engineering department in King Faisal University. Thank you, Dr. Professor Hisham, for joining us today, and we're glad to have you here tonight.
Thank you, Ali. Thank you very much.
You may have the mic, please.
Okay, so do you hear me well?
Yes, Professor.
Okay, just to correct you, I'm not a full professor. I'm just assistant professor. And yes, I graduated from McMaster University in Engineering Physics Department in Photonic major. So today we'll start talking about photonic devices and technology. If you have any question, you can stop me anytime and just ask the question. So do you see the PowerPoint presentation?
Yes, Doctor.
Okay. Okay, so basically I'll start talking about what is a photonic devices. Then I'll give two different examples about photonic devices, which is fiber optics and laser diodes. I'll talk about the working principle, theory, and how basically we make them. Then I'll talk about applications of these devices and marketplace and job opportunity for these types of technology. So what is a photonics? If you look at Wikipedia about the definition of photonics, basically you will find this. Photonics is the physical science and application of light, which is basically photon, generation, detection, and manipulation through emission, transmission, modulation, signal processing, switching, amplification, and sensing. So this is the whole definition of the word photonics. And photonics basically two parts. It's photo and then onyx, which is basically came from electronics. So it's photoelectronics, or some people call it optoelectronics. So basically the science of photonics talks about how you can deal with light, which is in this case photons. So people in light technology understand that light basically is a photon. So how we generate photons, how we detect it, how we manipulate the light, the emission, the transmission, the modulation, signal processing of the light, switching, amplification of the light, and using it for sensing. It all starts from light, and we all know the visible light range starting from 400 to 800 nanometer wavelength. So this is the visible range of light, started from the purple one, goes blue, green, yellow, till the red. After 800 or 760, for example, it will be infrared light. Before that, it will be ultraviolet light. And we all know the experiment that we used to do in elementary school when we used to put white light through a prism and we see the rainbow coming out of it. So believe it or not, this simple experiment gave a lot of information about light and light technology. Photonic device, however, are a component for creating, manipulating, or detecting light. So the photonic devices are devices or components that will generate or create light, manipulate the light, detect the light, and these can include the laser diodes, light emitting diodes, solar panels, photovoltaic cells, displays, optical amplifiers, and I add cameras, fiber optics, and so on. So many of these components basically are photonic devices. So today we'll focus into two of these devices, which is the fiber optics devices and the laser diode devices. To start with photonics, we have to define light, and people in this field understand that light is an electromagnetic radiation. In simple terms, basically, the light consists of electromagnetic waves, which is electrical wave combined with a magnetic wave. So if you have an electric wave will generate a magnetic field. Magnetic field will generate electric field, and so on. So electromagnetic wave basically consists of that, and light is part of the electromagnetic radiation. Electromagnetic radiation or electromagnetic spectrum span from radio wave up to gamma rays, going through microwave, infrared, visible light, ultraviolet light, X-ray, and gamma rays. As we go farther in this direction, the energy of the light will increase, the frequency will increase, the wavelength will decrease. So the wavelength will be very short for gamma rays and X-rays, for example, compared to the wavelength of the radio wave. Radio wave wavelength up to 1000 meter, and if you go down in the wavelength, basically you go up in energy, you'll go for microwave and so on. Electromagnetic waves basically has a very strong relation, the wavelength of it, very strong relation with the device or the element that generate this wave. For example, a radio wave, we need antenna, and this antenna could be goes up to 10 meters or so, because we need to generate radio wave in this range. But if you need to generate, for example, X-ray, you have to generate it through the atoms itself, because the atom dimensions in this range 10 to the power minus 10, which is the wavelength of the X-rays. Same thing for a visible range, for example. We generate visible waves from dimensions of about 1 micron or so on, half a micron, which is very similar to the human cell. And this is irony, because with the human cell, which is the eye, we can see the visible light. So all related together. So the wavelength related to the size of the element that generate or that can sense the wave. So let's talk about fiber optics. Fiber optics is a long, thin strand of carefully drawn glass about the diameter of human hair. Basically, it's like a human hair thin, and it's made out of glass most of the time. However, there's different types of fiber optics made of different materials. If we put a bundle of these fiber optics together, we make optical cables. It's used in different applications. One of them is optical communication. This is a graphical image of fiber optics cable. This is similar to the cables that goes under the sea. And this is actual fiber optics cable used for communication. And you can see light coming from this fiber alone. The rest of the fibers, there is no light coming from, or maybe it's an infrared. That's why we can't see it. This is a cable of fiber optics. You can see that light going through it from one side to another. I don't want to emphasize the importance of fiber optics in optical communication these days. You can see, especially in the Gulf area in Saudi Arabia, there is so many digging in the ground, putting fiber cables, putting fiber modules for communication. And you can see this in almost every city in Saudi Arabia. This is not only in the Gulf area, all around the whole world, you can see digging in streets, putting fiber cables in streets for optical communication. So how a fiber optics work? Basically, fiber optics depends on refraction, which is a well-known optical phenomena. And we can see that simply if you stick a rod or a pencil or anything in, for example, water, you could see at the interface between the air and the surface of the water, there is this rod looks like it's breaking. This broken rod, this phenomena called refraction. So the rod is refracted once it enters another media than air.
Sorry, Doctor, for the interruption.
Yes, please.
But the slides don't move. You're stuck with the first one.
I don't know why. So you can't see it? You can't see the slide here?
On the first one only.
Uh-oh.
The,
Hold on. What about now? Still the first slide?
yes, the first slide.
Okay, let me stop the sharing and then make it again. Okay. Why you didn't stop me?
I thought you were talking generally, then you will move, but then I realized then you were on the first page. Sorry, Doctor.
That's okay. Okay, let's do this. So do you see it now? Do you see the slides now?
No, it's the full page, the page of
Page of what?
StreamYard, the site we are using.
Okay. I don't know why it stopped sharing. Because I'm sharing screen here, so I'm using. What about now?
Yes, it's clear. Example on fiber optics.
Okay. So if I move the slide, do you see now new slide?
No, only the one with the example on.
So the slide did not change.
No.
Because I'm changing the slide here, and I don't know why it's not changing in your side. So it's still not changing?
No, still on the page, the page with the example one.
Okay. So any solution for this?
Maybe if you have a PDF file of the slides.
PDF file?
Yeah, I think it would work.
Okay, let me do that. I can do it PDF file, but it will mess up the arrangement of the animation. But anyway, I'll try to do it. Okay. Just hold on.
Doctor, did you try to share the screen, not the application window?
Share the screen? Yes, I did. I can do it again and see, because it's better to have that. Okay, let me try it again. Share the screen. Okay. Now I'm sharing the screen. Do you see it?
Yes, Doctor. Now we can move the slides. We can see the slides moving.
Great, great. Okay, so we start at this slide here. We are talking about how fiber optics work. We said that fiber optics depends on refraction phenomena. Refraction phenomena, basically, if you stick a rod or a pencil inside the water, you will see at the interface between the water and the air, this pencil or this rod looks like it's broken or bended. This phenomena called refraction phenomena, and it's defined using Snell's law. In Snell's law, basically, it tells us that sine theta 1 divided by sine theta 2, which is the angle of incident of the light. So if I have a light, and this light basically directed at the interface between medium number 1 and medium number 2, then the angle of incident of this light over the angle of refraction of the light that went to the second medium equal the speed of light in the first medium divided by the speed of light in medium 2, which in turns equal the refractive index of the medium number 2 divided by the refractive index of medium number 1. And refractive index in medium number 1 and 2 could be, for example, for air equal 1, for a glass equal 1.5. And once you have these two medium, then you can trace the light going from this medium, which is the first medium, to the second medium by this law, which is Snell's law. Now, you will find that if the light goes vertical to the surface of the interface between the two medium, then this light will not be refracted, because the angle of incidence at this point will be 0, so there is no refraction there. Once you bend the light and this theta 1 start to increase, then the refraction will increase and increase and increase until one wavelength, one angle where the light will be totally reflected back. So the light will be reflected back inside the medium surface, and no light will exit this surface. So this phenomena called total internal reflection, and at this phenomena, light will not be penetrating the surface to the other medium. Fiber optics depends on this phenomena, which is the total internal reflection, to contain the light inside the fiber. So the idea here, so I'll do it this way. So the idea here, if I shine light through a piece of glass like this, then the light, and in this case I have a laser light which give green light here. This light will, depends on the angle where I shine this light in, this light will be totally internally reflected inside the medium. So the light will be contained inside the media, and this is the idea of making fiber optics. Now, a piece of glass like this will contain the light for some distance, but at the end the light will be attenuated because the fiber losses at this case will be higher than 1000 dB per kilometer. In 1970, a breakthrough happened when fiber losses reduced to 20 dB per kilometer, and they managed to do that using what we call it step index fiber. Step index fiber, basically, they make two medium of glass to contain the light. The first medium here, it's called the core of the fiber. The second media, which around the core, will be the cladding. So if you come with a certain angle that make total internal reflection, then this light will be contained inside the core area and it will not escape the core area to cladding. Now, the difference between the core area and the cladding area is basically in refractive index, and the difference is very small. So, for example, if the core area refractive index is 1.5, then the refractive index of the cladding will be, for example, 1.497 or so. And this small difference between the two makes the step index fiber that will make the losses go very small compared to the previous type of fiber. So now we can make a fiber like this using core and cladding, and if we come with a right angle, then we will have a total internal reflection inside the core area, and the light basically will be contained inside the core. This way we can contain the light for very long distances, and nowadays basically we make communication between for example, US and the Middle East using fiber optic cables under the sea using this phenomena. So is the slides changing now?
Yes, doctor, they are changing.
Great. So how we use fiber optics in optical communication? Basically, if we need to communicate between 2 points, point number 1 and point number 2, basically what I do, I connect them through fiber optic cable. So I have fiber optic cable, connect these 2 points, and according to the distance between these 2 points, I can make communication, the quality of the communication, the speed of the communication, bit rate, and the distance. All of that is considered in this case, and optimization is about how we can make fast communication for very long distances. So in 1975, the most advanced coaxial system was established with 247 megabit per second. So before fiber optic cables, people used coaxial systems and microwave. The maximum limit people reached communicating with these two types of communication is 274 megabit per second, which is a very high bit rate. However, posting stations needed for coaxial cable every 1 kilometer, which basically translates to cost. Same thing for microwave. Posting distances is better. However, the bit rate is smaller. So for microwave bit rate less than this, but posting distances could be 50 kilometer or so on. So this is the history before people starting fiber optic communication. So the need for fiber optic communication came from these three advantages of fiber optic communication. The first one, high bit rate, L product. So we need high bit rate and distance. And people usually in this area, in this field, mark it as PL product. They call it PL product. Bit rate, distance, product. Because I need high bit rate and I need long distances. So the product of these two is a number that we need to calculate to compare between different types of communication system. The second advantage of fiber optic communication is the immunities from electromagnetic wave interference. So with coaxial cable and microwave, electromagnetic interference is inevitable. People tried many times to minimize the interference, but I remember these days when I used to talk over the phone, and while I'm talking over the phone, someone basically entered to my talk, and I hear people talking, different people whom I shouldn't hear, and they shouldn't hear me also. But this is because the electromagnetic wave interference. Together with that is data security and transmission. Security and transmission of data is very important. With fiber optic cable, it will give me this needed security for transmitting the data, because you can't basically interfere with the electromagnetic waves of the fiber optics. The only way to hack the system, basically to cut the fiber optics, tap into this fiber, and then start streaming data from there. However, the technology now can easily find that there is someone basically tapping to your system and taking information from that. So just I give you a brief history about fiber optics. In 1950, they found that the PL product will be higher if we use light wave. If we use fiber optic communication, the PL product will be higher compared to the coaxial cable and microwave. So the need at that time to make light wave technology, basically we need coherent optical source and transmission medium. يعني بدنا fibers وبدنا السورس الoptical source اللي make the optical communication. In 1960s, the first issue was solved. Basically, coherent source were invented. Solid state lasers and semiconductor lasers at that time were invented and demonstrated. In 1966, it was suggested that optical fiber could be the medium. However, as we said, the losses of the fiber was greater than 1000 dB per kilometer. This problem was solved in 1970, where the breakthrough losses went down to 20 dB per kilometer when they invented the step index fiber that we explained in the previous slide. At the same time, gallium arsenide laser running continuously at room temperature were demonstrated. So now the two needs for optical communication, which is the coherent optical source and transmission medium, were available in the 70s. So optical communication started from the 70s until now. Nowadays, we reach a bit rate distance product up to 10 to the power 7, which is basically we are talking about 10 giga systems, which is a very high speed optical communication. So this is just a historical perspective. In the electrical era, a telegraph in 1836, telephone 1876, coaxial cable 1840, microwaves 1948. Then the optical era came in 1978, first optical communication generation, optical amplifiers 1990, wave division multiplexing technology started in 1996, and multiple bands communication technology in 2002. Nowadays, we have systems that are capable of going up to 200 terahertz at wavelength 1.5 micrometer for optical communication. So how fiber optics fabricated? Fiber optics fabricated in a very simple, however, it's very precise technology. Basically, they make the fiber optics from glass. So they have a glass. They make the fiber that they draw it from with two types of glass with slightly different refractive index. So the inner side of the glass has higher refractive index than the outer side. And this glass, this one or this one here, or this one when they make it here. So this is how they make the cladding and the core area. by heating it and flowing different gases on the glass, so the refractive index will be different between the center and the outer diameter. So they take this glass rod and they put it in a vertical assembly where they heat the edge of it here. And once they heat the glass will be softened. Then they can basically draw this glass. So they pull this glass and draw it. So this glass will start to be thinner and thinner until it reaches like a human hair. Then there's a thickness monitor system. Then they coat this glass with certain coatings for protection, and they put it through a curing system or curing oven. Then they pull it and basically put it in a drum to make basically a drums out of it. So this way they make fiber optics. This is the symbol. However, it's very critical and very precise technology to make fiber optics, and all basically from glass. Fiber optics nowadays is drawn from different types of different shapes, like this one here, this shape in the core area, this shape in the core, or this shape, different shapes according to the need, according to the type of fiber optics and what they need or what they want to make out of it. Types of fiber optics, basically, as we said earlier, the slab piece of glass, which has a very high losses. Then we have the step index fiber, which made it possible to make optical communication out of it. Then they make graded index fiber, and this graded index fiber solved some disadvantage about the step index fiber. And then they went for a single mode fiber, and using a single mode fiber, nowadays we can communicate between continents. So between the Middle East, Europe, and North America, and so on. In simple terms, single mode fiber basically improved a lot compared to the graded index fiber and step index fiber, and it basically makes the losses very small. Nowadays the losses is 0.2 dB. However, the development now for optical communication and fiber optics evolve around attenuation, dispersion, and polarization. So these are the main development techniques and issues that people tackle to improve the fiber optic communication systems. So enough talking about fiber optics. Let's talk about laser diode, which is the example number 2. So what is a laser diode and how it looks like? What we mean by quantum well laser diode, and how we can make multiple quantum well laser diodes. So let's see how a laser diode looks like. Basically, a laser diode looks like this. It's from its name, it's a diode. And a diode, for people in electronic field, understand that diode is basically a p-n junction. So you have a p material and n material, and once you stack them together, you will make a p-n junction, which is a diode. Now, if you need to make laser out of it, this diode has to be from a material called direct band gap material. For example, aluminum, gallium arsenide, or indium phosphide, or gallium arsenide, or indium gallium arsenide phosphide type material. So these are the materials that people use laser diode out of it. So if you stack p-type material with n-type material and you inject current through this diode, then you may generate a laser light out of it. A laser light will come from the area in between the P and the N, which we call it the junction area. And most of the time, this junction area is a third layer. People or photonic designers design it to make light coming out of it. This diode will be put in a can type basically package, or different type of packages, but this is a can type package that they put laser in it, and these the electrical connection for this laser type. So this is basically a bulk type laser. Now, a lot of studies and research is going on in this area, where the active area of the laser, where the light coming out of it. This active area could be a bulk, for example, aluminum gallium arsenide or indium gallium arsenide material, or it could be what we call it a quantum well type material. So if it's a quantum well type material, it will be something like this. So these are the stackings for a laser diode, which has many layers of N and P type layers. So the top layers here is the P type, the bottom layers is the N type, and the middle layer here, what we call it the quantum wells. Quantum wells comes in from different materials. You can see here, for example, gallium, antimonide, aluminum gallium arsenide, antimonide, and so on. So there's different types of material that people use. At the end, we have to put metallization for electrical injection. So here, this is the stacking of metallization, starting from ti platinum gold. So we use titanium, platinum, gold for metallization on the top layer, and the back layer is ti platinum gold also for backside metallization. Then the wire will be connected from this top layer and bottom layer for the plus and minus connection of the power supply. Usually, there will be a silicon dioxide isolation layer just to isolate the whole area here and allow for the current to go through the system just from this ridge area to contain the light coming from this laser to be from this side only. This red layer here called the active region, and this active region could be bulk, basically just a slab piece of indium phosphide material or gallium arsenide material, not doped and sometimes doped slightly. It could be a single quantum well, it could be multiple quantum well. So this is a real image of a laser diode, and this laser diode basically compared with a needle eye. You can see how small this laser diode, basically it's smaller than the needle eye. You are talking about 300, 400, 500 micron dimension, which is less than 0.5 millimeter. This is a laser diode basically in a package, and you can see the laser diode basically is this black piece here, this small black piece, and these are the electrical connection for this laser diode. This laser diode is put on top of a stacking of heat-controlled environment to control the temperature of the device. Now, this package could be put in a package like this one, and these are for electrical connections, and this line here is the fiber line to transfer the light. Now, you could stack so many of these laser diodes and make them in one stack like this. You put many of them, and once you put many of them, you can generate high energy laser system. So, as we said, these are the stackings of the laser diode, and the active area is in this region here. So this is the active area. Now this active area, as we said, it could be one single quantum well, and if it's one single quantum well, then we could get lasing like this. So this is the spectral coming out of this laser system, and you can see the light coming out of it, lasing at this wavelength here. So if you look at this wavelength, it's around 1520 nanometer, 1520 nanometer or so. This figure shows as you change the injection of the current of the light to the laser, you could see the effect of that. So basically at 22 milliamp, there is no lasing there. At 72 milliamp, now it starts to show some hump here. Then at 141 milliamp, you see lasing here. And this is the lasing peak at the higher gain media. And then as you increase the current, the laser will start to show and a clear distinction of single wavelength lasing at this wavelength here. So this is when you use a one quantum well. People use more than one quantum well, so they go for multiple quantum well, basically to widen the gain. So if you look at the gain peak of the laser looks like this for a single quantum well. If you have two quantum wells, then the total gain peak will be something like this, and this will give more wavelength than the other one. So if we tune this laser, we can cover more wavelength than the first one. So that's why people go for different multiple quantum wells. And here in this structure, we used 5 quantum wells, and we got a very wide range of gain peak and gain profile. And from there, we could tune this laser around 100 nanometer range. Now, there is a model, electrical model and optical model for how we basically simulate these types of devices. It starts from Poisson equation, which for those who are familiar with Poisson equation, basically it's the divergence of the electrostatic potential equal rho, which is the charge density, which is given by this equation here. And also we use the electron and hole continuity equation to basically to solve for the electrons and holes availability inside the device. These 3 equations, if we solve them together, we make the electrical model, and sometimes we combine them with the thermal model, which is the heat equation also. This will give a full model for the electrical and thermal property of the devices. For the optical property, basically we have to solve the wave equation. And it's a tedious process. People use a lot of theories there. In our group in McMaster University, led by Professor Dan Cassidy, we developed the KB simulation tools, and I had the opportunity to basically verify the results of this simulation tool using the experimental data. And we did a lot of structures for quantum wells, and we used it for certain applications. So here's some of the structures that we used to do in McMaster University. This is a multiple quantum well laser structures, and each one of these has its own advantages, and it can give me different gain profile. Now, there is different studies about which structure is better than the other one. For example, people say the dimensionally quantum wells better than the compositionally quantum wells, or combine both is better. However, there is no one favor on the other. There's just different opinions, but there is no solid evidence shows that this is better than the other one. Here's one of the 5 quantum wells that I talked to you about, and this is actual data. We verified it using experimental data for the tuning spectrum of the of this quantum well laser diode. This is the actual measured gain profile, and you can see the gain is flat, basically at around 180 milliampere injection current. So basically, I can tune this laser from almost from 1600 to around 14 1480, 1490 continuously, and I can use it in different applications. The power profile of these lasers basically resembles the equation of the power given by this equation here, and it's basically similar to the IV curve of the diode. However, this is the output light of the diode. There is a threshold at certain injection current. There is no light or very small amount of light coming because it's still not lasing. And once you reach the threshold, the laser light will be generated, and then you can have almost exponential increase of light energy. These lasers are tuned in different techniques, and for those who take fiber optics with me, maybe they learned about different techniques today. But in simple words, there is different techniques in tuning these lasers. If you put an external cavity diffraction grating, you could tune these lasers and make them tunable, and you can select any wavelength you want. There's a different version of this grating, which is, they call it the diffraction optical element, and it's a very simple technique. Basically, if you move the diffractive optical element back and forth, you tune the laser. However, this technology and this technology need a mechanical movement, and nowadays people went for electrical tuning, which is what they call it split cavity or cleaved coupled cavity. So they cut the laser in 3 pieces. The medium piece, basically it's the lasing piece, and the 2 other sides are the control sides. This is an actual split cavity laser under testing, and you can see the 3 pieces, which is 1, 2, 3, that generate and control the light. This technology is still under research, especially for very long range tuning. However, for short range tuning, 10 nanometer, 20 nanometer, it's available nowadays, and people use it in optical communication. This is a laser tuning curve that we did experimentally at McMaster University. And you can see here we tune it from 1490 up to 1610, which is about 120 nanometer, which is a very wide range of tuning that using one single laser, we can make this range of tuning is very amazing compared to the available research around the world. Marketplace and applications for these lasers. We usually look at the laser focus world. This give estimate and give statistics about the marketplace of the lasers. And if you look at the last version of the laser focus world, taking the information from this website here, basically estimated $16.6 billion marketplace for this technology. And this is only just for the lasers, not for the fiber optics technology. Fiber optics technology maybe double this number or so on. The sectors for this technology, you can see it in different areas here, in medical applications, entertainment, displays, printing, material processing and lithography, optical communication and optical storage for like hard drives and so on, scientific research and military. All of these are the sectors that people invest in this technology. So if you would like to pursue your education in this field, you can see where is the major basically jobs opportunity in this area. For example, in material processing and lithography, it's a huge portion of the market. And then in the optical communication and optical storage, it's also the second huge share. and then military and scientific research is the third. Then comes instrumentation and sensors and the rest of the area. So, for example, in material processing and lithography, this is one of the laser CNC machines that cut using fiber optic lasers, cut metal, and I saw machines in YouTube that cut metals around 3 centimeter and above. So a 3 centimeter thick metal, you can cut it with a laser fiber system, which is amazing. So you can cut, you can drill, you can shape different types of material using this technology. This is the market share up to 2020. It's $6 billion in this market share. Also lithography and system processing and material processing, making like nanoparticles, nanotechnology, and things like that. It's a big share in this field. For the communication, we all know that the whole world is going for optical communication now. Optical fibers, laser diodes, and data transfer and data storage all is a big hit now, and people use it. The marketplace around $4 billion in this share. So this is a very good opportunity for you to find a job in this area if you need to go in this field. Military, it's a very important field. And when we talk about military for photonics, we are talking about range finding, tracking, targeting, laser missile systems, and so on. All of that basically the address for advanced countries. So if you need to be advanced, if you need your country to be advanced, you need to invest in this area. And to invest in this area, you need photonics, basically, to be well known in this field, because here where you can make advances. A market share up to 2020, it's $2.2 billion. So it's a big portion of it. And actually, these days, and maybe you all know and see the Azerbaijan-Armenian war, you could see how this field played a big role in Azerbaijani basically declaring winners in this war because of this technology that they acquired. For instrumentation and sensing in the Gulf area here, we are an oil and gas country. Technology evolved around that, so there is a big share and a big market for oil and gas industry. And if you need to work in this field, you need instrumentation and you need sensing. So lasers and optical communication is used here for target detection, missile deployment, for example, for sensing, bioinstrumentation for bio and chemical sensing, and for the oil and gas industry, metrology, for a lot of sensing. And for example, in the market, you need barcoding, readers, and other sensors for environmental sensing. All of that comes into the instrumentation and sensing industry, and this is around $1 billion market share. Last but not least is the medical application, and the photonics in medical application evolved around $1 billion industry, where devices like optical coherence tomography, like this device here, is used for like for retina scanning and skin scanning and laser surgery and other types of systems. For example, here, eye and vision treatment, hair removal, all of that is using photonic technology for that. So by this one, I'll stop and end my presentation. So today we learned about a few things about photonics, about lasers, and about fiber optics. How we make them is another story, and we'll leave this to maybe a next seminar, inshallah. So by this, I
Thank
end my
you.
seminar. Thank you.
Yeah, thank
If you
you,
have
Dr. Hesham.
any questions.
Yeah, now we'll see if there are any questions. Yeah, we have a question from Mohammed Al-Tawa. He says, what is the properties that affect photonic devices and that produce photonic devices efficiency, I think?
Wow, this is a very wide question, actually. When you talk about properties that affecting photonic devices, there's so many properties that affecting the photonic devices, but it depends about the device and what you need to do with it. For example, wavelength of the light coming out of optical devices depends on the material that you use the device. Properties also like temperature. Devices, photonic devices affected hardly by temperature. So temperature control and temperature maintaining is very important if you need to use photonic device, especially for optical communication. Development are going on, research going on how we can make devices not affected by temperature. However, most of the time you get hit by the physical limits of the material that you're using and by certain like nature laws that you can't get away with. By efficiency will never exceed 100% and so on. So I hope this answer your question.
Thank you. And now we have another question from Dr. Rahman. He says, what's the relation between photonics and quantum computing?
Okay, well, as you can see from my slides and my presentation, photonics basically we are talking about optoelectronic devices. Now, I'm not, very strong in quantum computing and understanding what basically they mean by quantum computing, but the dream always that people can make basically optical computer. So nowadays the computers that we have is made out of electronic parts, and what runs inside the computer is electrons, and that's why we call it's an electronic device. Since people found out that photonics is the way to go, and light wave technology is the way for high speed, high communication, fast communication, and so on. So their dream now is to make an optical computer. Now they can't do it because the technology is not mature enough yet, but people are working in this direction. So just to finish my answer about quantum computing, basically you go for quantum effects to use it for computing. And just to define the quantum effects in simple words, if you go with the material dimensions very small, smaller than 100 nanometer range, so the dimension of the material that you use for example, for computing and so on, if it goes below 100 nanometer range, then you get quantum effects. And if you employ and use these quantum effects for quantum computing, then you can make faster computers than what we have now. So combined quantum computing and photonics together, we can make what we are looking for, which is the supercomputer that we need for the future. So this is what I can tell you about photonics and quantum computing field.
Thank you, Doctor.
You're welcome.
And are there any questions? I think that's it. Thank you, Dr. Hesham, for the interesting session. And
thank you.
we have a certificate we will for as a gratitude from our branch. So I will share it to you.
Sure. Thank you very much.
Here it is, and we will send it shortly to you.
Okay.
And thank you all for coming today and for joining us. And sorry for any technical issues we had in the beginning. And please fill in the attendance form for the certificates. Thank you. Dr. Sham, do you have any last words?
Oh, just I wish you all the best, and think photonics. In our Middle East area, we need people with photonics.
Yes, thank you. Okay, see you later.
Thank you very much. Thank you. Have a good night.